Limiting reactant. If you were to make chocolate chip cookies, you need two principal ingredients. You need the cookie dough and you need chocolate chips. When one of these runs out, well, that's all the chocolate chip cookies you're going to get, even though you might have more of one of the ingredients. Whatever runs out is called the limiting reactant. If you had a candle that was burning, it would combine with oxygen from the air to form CO2 and water and maybe some soot and maybe some carbon monoxide. If you were to let the candle burn until it went out, the reaction has stopped, and most likely the candle wax would be the limiting reactant. Lots of air still available with oxygen, but the reaction can't continue because one of the reagents has been all used up, and it's called the limiting reactant. Let's apply that concept to an equation. Here we have an equation representing the burning of methane combining with oxygen to form carbon dioxide and water. And here's a typical problem based upon that balanced chemical equation. If we were to react 30 grams of methane with 100 grams of oxygen, how many grams of CO2 form? Well, I see numbers. That suggests to me a math problem. I don't have a formula for working this problem, so we'll be using the factor unit method. But it's a little bit different than some of the factor unit method problems we've worked before because we have two starting materials. And that's my clue that this is going to be a limiting reactant problem. We have to work two problems. We'll see how much carbon dioxide we can get from 30 grams of methane if we were to use all of it. And in the second problem, we'll see how much carbon dioxide we can get using the 100 grams of oxygen. So let's work those two problems. Using the factor unit method, step one, we'll write down the number that's given and its unit, 30 grams of methane. Step two, we'd like to know grams of carbon dioxide. I've left space for a factor. And it's always true, as we work these in one step, that the unit of the answer, grams of carbon dioxide, will be up here in the numerator. Grams of methane will be down in the denominator, so that as we multiply, it cancels, and we're left with the unit that we're after. We get these numbers from the balanced chemical equation by interpreting it in terms of moles. And the number in front of CO2 is 1. It's abbreviated, left out, but that coefficient 1 indicates 1 mole of CO2. And to convert that to grams, we'd use the periodic table. Carbon is 12 atomic mass units, 2 oxygens would be 32 more, or a total of 44.0 grams of carbon dioxide. In front of methane is the coefficient 1, and converting that into grams, we get 16.0 grams. Multiplying 82.5 grams of CO2 are possible when we use 30 grams of methane. Let's look at the oxygen calculation now. Using 100 grams of oxygen as the starting material, we'd like to know grams of carbon dioxide that we can get if we used all 100 grams. I need the unit of the answer in the numerator, the unit that we're given in the denominator so that it will cancel. Again, we get these numbers now from the balanced chemical equation. As we did before, we have 44 grams of CO2 in the numerator. Down in the denominator, in the balanced chemical equation, there's a coefficient 2 in front of the oxygen. Oxygen is 16 atomic mass units. 2 oxygens would be 32. Then 2 moles of O2 would be twice that, or 64 grams. Multiplying this out, we get 68.8 grams of CO2. And that's a smaller number than what we had before. And in limiting reactant problems, it's the smallest number that wins. 68 beats out 82, because when we get 68.8 grams of CO2, all of the oxygen has been consumed. And even though we could theoretically get more CO2 if we had enough oxygen, we don't have that oxygen, and so the reaction stops. That means that there'll be some CH4 left over, O2, or we could say that CH4 is there in excess, O2 is the limiting reactant, and 68.8 grams of CO2 is all that we can get. We could say it's the maximum amount that could form, because all the O2 would be consumed. Let's go ahead and calculate how much water we could get. We know now that O2 is the limiting reactant, so we won't bother working the other problem. We'll just use O2 as the starting material. We'd like to know grams of water, so the unit grams of water will be up in the numerator. We'd like to get rid of grams of oxygen. It's down in the denominator. We get these numbers from the balanced chemical equation by interpreting it in terms of moles and then converting moles into grams. There's a coefficient 2 in front of the water in the equation, so we need 2 moles of water. 1 mole is 18 grams, 2 moles is 36 grams. This number 64 is the same that we used before. Doing the calculation, we get 56.0 grams of water. And just for fun, let's add these two numbers together now. 56 grams of water, the 68.8 grams of CO2 that we found could be formed, that totals to 124.8. We started with 130 grams of reactant. That means that 5.2 grams of methane are left over. Has to be a conservation of mass. If we started with 130 grams, we have to end up with 130 grams. So we have a mixture of water and CO2 and some of the leftover CH4.